opportunity for presenting AERPAW. I think I have about 15 minutes. So I will just have a quick overview of AERPAW and then give some example experiments that we have been working on and planning to do for the rest of the year. As you all know, AERPAW has the goal of being a unique technological infrastructure for serving advanced wireless and unmanned aerial systems researchers nationwide. At the heart of the project, we have programmable radios, similar to all the other PAWR platforms, but we bring in the picture the programmable mobility, where we program the locations and trajectories of vehicles on a programmable network. I will be quick on the overview. So you can find most of these information on our website and user manual if you go to aerpaw.org. So I will talk about some key components of AERPAW. We have this so-called fixed nodes in AERPAW, which is our outdoor footprint. And during phase one, which ended last November, we have deployed 3 fixed nodes. These fixed nodes are either light poles or rooftops or towers that we are purchasing and deploying. So we had one of each during phase one. And next to fixed nodes, we have the so-called AERPAW fixed radio nodes. These are radio equipment in enclosures or antennas that are going up to fixed nodes. During phase one, we primarily deployed software-defined radios. We have 4 SDRs for each fixed node. One of them is for spectrum compliance monitoring, but the 3 others are different types of USRPs that you can program. And we also deployed other equipment, Ericsson base station, Keysun RF sensors, LoRa, Facebook, and we have a compute node, which is a Dell server in those fixed nodes. So during phase one, what we have opened for external access are SDRs. We are still working on operationalizing and opening access for the other equipment, which will happen by the end of this year. This shows the fixed node footprint we have currently and what we plan to have during phase 2 and phase 3. Like I said, as of November last year, we have wrapped up phase 1. We have 1 fixed node in where we call the Lake Wheeler Field Labs, which is more rural area where we primarily fly the drones. And we have 2 more fixed nodes in our Centennial campus within about 300 meters separation of each other. And during phase 2, we are now deploying 4 more towers in Lake Wheeler. These are towers like you see in this picture here. So they will be, their construction will be finalized by the end of this summer, and we will be populating them with the radio equipment and operationalizing and giving access to our users by the end of this year, which we hope to finalize phase 2. And this shows our fixed node in Lake Wheeler. You can see the antennas at the top that are connected to USRPs. This is a bit older picture, but we also have Ericsson radios that are connected to here. We have been doing a lot of experiments with them, and the drone nearby. And in addition to fixed nodes, we have vehicles, and the vehicles are obviously temporary. They are taken to the experimentation site only when there is an experiment. And our vehicles are unmanned aerial vehicles and unmanned ground vehicles. We also purchased a helikite that we will integrate into our platform during phase 2. So we have 3 UAVs and 1 UGV during phase 1, and we will be having many more during phase 2. What we attach to these vehicles are so-called AERPAW portable radio nodes, or APRMs. They look like this. It's a small box with antennas sticking from them, and it's like a multi-layer sandwich that you have radios, control equipment for the vehicle, and compute node. And what we have in these portable nodes is initially we have, again, SDRs, smaller versions of these. We have 2 SDRs in each APRM. One of them is, again, for spectrum compliance monitoring purposes, but the other is available for experimenter. And we are also looking into integrating mobile phones and sensors in these portable nodes. So they will be able to support primarily 3 different types of radio equipment. And we have an Intel NUC as the compute node, which runs, again, similar to other platforms, containers and Docker. So we have the experimentation software running in this Intel NUC, and along with our control VM. And this shows our vehicle, which is a UAV, and along with the portable node attached to it at the bottom. It's the UAV is fully developed in-house, designed and developed and assembled at NC State. And you can see a whole bunch of different links. Experimental link is just one of the wireless things coming into this drone. We have GPS, we have a cellular modem for backhaul for control purposes, RC, telemetry, and etc. And the Intel NUC that you see on here, the experimentation software runs on that, and it has the full control on where the drone goes, right? So the experimenter programs the drone, the pilot just is a safety pilot. The drone behaves whatever the experimenter wants the drone to behave like. And it's the same thing for the UGV. So you can take the same portable node from the drone and attach it to the UGV. Now the portable node starts controlling the UGV, there's same interface to interact with the vehicle control. And finally, we have the virtual nodes and the sandbox and the cloud environment. So we have servers in our AERPAW cloud where experimenter is initially expected to develop the RF and vehicle software through an emulation environment. We have been posting many different example software, both for radio and vehicles, in our user manual, and experimenters can start with them and do emulation in the cloud first. And then once they're ready, I have a next slide actually on the workflow. We take it from there and we execute the experiment. So this cloud environment doesn't have radio hardware during phase one. During phase two, we are integrating a channel emulator along with many different SDRs and other wireless equipment to be integrated into our development environment. And this shows our workflow. The experimenter joins the platform through the portal, asks for resources, fixed nodes, portable nodes, radio equipment, initially does the development in our cloud. And once they are ready, the experimenter hands over the software, radio, vehicle, and traffic software to AERPAW Ops, and the AERPAW Ops executes the experiment in the field and then returns back the data to the experimenter, and it may iterate from there. Experimenter can further improve and do the testbed experiment again. So this is the default mode is what I just described is the program it yourself approach. So it's free for academic users, for industry, depending on consortium we may charge. We also have other modes of experimentation, experiment as a service, experiment development as a service. These may require more effort from the AERPAW team. Live limited access. We are now, for example, integrating Keysight RF sensors to the platform, which we are planning to give limited live access to collect the passive spectrum data or IQ samples from the environment. That will be by the end of phase two. We will finalize the workflow and open it for use, and also obviously bring your own device, which requires more back and forward with the experimenters. We can support your equipment, but we have to review how it will integrate with our workflow. So they may have different obviously challenges and amount of work, so some of them may require some additional funding. So this very quickly, our timeline, we finished phase one in November. We are scaling up and adding new capabilities in phase two and further scaling in phase three. By the end of 2023, we hope to finalize our deployment, and then the rest is operations. So I talked about the example experiments in AERPAW. If you go to our user manual, which is accessible also from aerpaw.org, you can see many different sample experiments that we posted. They have been tested by the AERPAW team, both in the development environment as well as the testbed environment, along with drones, both the radio and drones. For phase one, we have these 5 experiments, LT with both SRS and OAI, and also LT cell scan, and 2 GNU radio experiments. In the user manual, there is description like this. It talks about experiment overview, different variations in emulation and testbed, and specific instructions on how to run them. And then in phase 2, we are adding several other example experiments. They will be added all by the end of this year. to our user manual. So they will be again tested and executed both in emulation and testbed, and probably sandbox by the end of phase 2. So they will be readily available. The users can start with any of those and then can add new features. Whatever research they want to do related to these, they can test, especially with drones, which may give some different propagation environments. We are also including other equipment than SDRs, Ericsson, Keysight RF sensors, and Facebook. We are also working on example experiments related to these additional equipment. The experimenter will be able to follow the instructions and execute these experiments. And you obviously also have vehicle control software running. QRAD control is to create and edit mission plans. What we don't have yet as an example experiment is autonomous navigation. Right now, the user just gives waypoints. When I say autonomous, I mean the drone will be able to make decisions where to go based on some wireless observations, for example. So that's also going to be included by the end of phase 2. So I will just quickly give an example of an experiment that we have done last summer, and actually did more variations in fall. So the UAV flies on a predetermined trajectory, and in the meantime, it logs key parameters of interest with timestamps and location tags. And we use SRS-RAN for this. We can use any of the others, GNU Radio or OAI. But for this experiment, it's just SRS-RAN. And initially, this experiment is developed in emulation, then executed in the testbed, and then you can compare those two results. So this shows some videos captured by a second drone of the drone in action. The drone takes off, goes to a certain height, and then follows a linear trajectory. There are waypoints that the experimenter defined in the emulation mode first, and the drone goes over that trajectory up to a certain point, and then comes back to the initial takeoff point. You can see this yellow square on the ground and our tower here for Lake Wheeler 1. And then it lands back, and we repeat the same experiment with the UGV as well. Again, the software is the same, the way that it interacts with the drone and the UGV. It's just not obviously flying too, so the altitude is 0. And then we compare what we obtain with UAV and UGV, and also with the emulation and then the testbed in the real environment. So this is a close-up view of the trajectories, goes to a certain altitude, follows a certain path, comes back and lands. And the way that we currently have our emulation is it has a very simple path loss model, which is a disk model, even not free space. So after the UAV goes outside of a disk, it's disconnected. Free space is obviously easy to add, that's being done, but adding realistic provocation models is a bit more trickier. So that's one of the things that we will work. But you can see the same behavior both in emulation and testbed. As the drone goes even in the testbed, the drone goes outside of a certain range, it gets disconnected. It stays like that for a while. When it's on the way back, it gets connected again. And when you look into the data in the emulation and testbed, you can see that this experiment was about close to 4 minutes, 240 seconds. And you can see the way that the experimenter designed the experiment in emulation, the vehicle behaved in the same way in the testbed. You can see kind of the waypoints, kind of deaccelerating and accelerating again in between waypoints, goes to a certain point and then returns back. And this shows the altitude for the drone. Again, similar observations with testbed and emulation. The radio data, it was a very simple experiment, like I said, to send ping messages, and the experiment was logging the delays for those pings. You can see that both in emulation and testbed, when the drone was within the coverage of the tower, which is running the SRS-RAN base station in LTE. So the ping delays are very small. As soon as it goes outside of the coverage, the delay increases, and then it comes back again. So we have very consistent observations between emulation and testbed. And this one shows the received power versus distance. It doesn't consider emulation. Like I said, the emulation has a disk model for now, but 2 different experiments. You can see that as you go away from the base station, your receive power reduces, but because of path loss or antenna mismatch, these are dipole antennas and you have some altitude mismatch with the base station. So you have receive power fluctuating over time. And at this distance, you can see that the power is also, even though the distance is the same, your altitude is changing, you can see that it may significantly affect receive power, even though you're at the same distance. So just some examples on types of experiments that can be done in the 3D environment. And one experiment that we are working on now, hopefully this will be done within the next month or 2, is to densely capture the signal strength data in the Lake Wheeler farm using the drone. So we have a dense mesh that we will traverse with the drone. So it will basically fly at the same altitude and capture RSRP data, for example, and maybe some other key parameters of interest. And then we will do this at whole bunch of different altitudes and across the whole field. And this will give us very useful data to analyze the antenna effects, multipath radio environment maps. We are doing this in the context of nation radio dynamic zones. There is a lot of interesting work that we can do for sparse signal processing to extrapolate the data across the whole field. And we have the precise control on the exact location, and we know where we collected the data. So I think that's a very powerful feature that we can support for experiments. And another example experiment we have done recently, and I have 2 slides left.
If we could wrap it up, that would be great.
Okay, sorry. So this is from last year, but we are repeating this actually this week. The whole week we are collecting data from baseband to 6 gigahertz across the whole band with our spectrum compliance sensors. And we are comparing them with the common 4G and 5G bands. You can see there are cellular bands here, non-cellular bands. And once we have this data at the 3 different locations, we may do some interesting analysis, like we can even triangulate maybe some locations of base stations. So this is my last slide. If you have questions, you can contact here. So we have a bunch of other experiments lined up. I think we may discuss this in the panel too, but we are looking into doing some experiments with this infamous altimeter coexistence issue in the C-band with an Android phone, smart agriculture experiments with the Ericsson base station, multi-band aerial connectivity with UAVs. So with the SDRs, we can support multiple bands. And this is a nice example for type of experiments that industry showed interest. This is a BVAC IUCRC project we have at NC State, and also spectrum occupancy with UAVs. And we are looking into moving to 5G. We are developing the example code. There are challenges when there is mobility, but we are trying to tackle those. And autonomous control, UAV swarms, tracking of UAVs by passive recognition of UAV signals. And we are also, LoRa is one of the directions that we are pursuing along with Purdue. So I'll stop here.